and these testing methods will be discussed in another program. There are many methods to correct a resonance problem. Although it is not always possible, the simplest method is to simply change the operating speed of the machine. If the machine is running in resonance, simply increase or decrease the speed to move out of the amplification range. Notice that in this rotor kit, the vibration amplitude drops considerably when the machine is running faster or slower than the resonant frequency. Remember that we have pointed out that resonance is only a problem when there is a forcing function equal to the resonant frequency. So simply remove the forcing function. If the resonance is at 5 times shaft speed and the pump has a 5-vaned impeller, change it to a 7-vane impeller. The forcing frequency will be removed. If resonance on a fan is at blade pass frequency, change the number of blades on a fan. If the resonance is equal to the frequency generated by a coupling, change the coupling type. If the resonance is a multiple of the belt frequency, change the shib size or belt type. Adjusting the machine speed or changing the forcing frequency are the two simplest methods to correct a resonance problem. Other methods can be used that affect the resonance, that is, adjust the mass, the stiffness, or the damping. Adding stiffness increases the resonant frequency. Adding mass decreases the resonant frequency, and adding damping reduces the amplitude of the resonant frequency. Let's take another look at the guitar example. As we increase the stiffness by tightening the string, the frequency also goes up. If we strike a more massive string, the note is lower. Applying damping to the string decreases the amplitude. Let's add mass to our cantilever beam and view the resulting coast-down data. The data shows the peak vibration at 1509 RPM, which is equal to 25 Hertz. This is a decrease in frequency from our previous tests, which showed a resonance at 26 Hertz. Let's see what happens when we add damping. We will use this disc attached to the system and immersed in oil as the damping. Now we will monitor the coast down to see the effect of this damping. Notice the amplitude of our peak is decreased. The frequency has not changed significantly. These structural modifications affect your plant's machinery in the same ways. However, using a trial and error method for making modifications often leads to an incorrect solution.
Lots of people have increased stiffness and at the same time increased the mass and wondered why the frequency didn't change. If the stiffness increases and you add mass to do that, you really haven't done much to the natural frequency.
Before making permanent structural changes to a machine, it is often recommended that a modal analysis and/or a finite element analysis be performed. In this program, we examined in detail the characteristics of resonance and many single-channel analysis methods for resonance detection, as well as introducing the benefits of multi-channel analysis techniques. Our interview guest, Mr. Art Crawford, pointed out that resonance could be the #1 machinery problem in industry today. Resonance can elude the analyst, so perform several tests to confirm its presence and determine the source of the forcing function. When using normal averaging for a bump test, the machine must be off. Use the negative linear averaging for the bump test when the machine is running. The peak hold coast down provides good data, but take into consideration nearby machinery and background noises. Remember, phase data is often the key to verifying a resonant condition. We are confident that the application of the principles in this program will help you successfully detect system resonance. Thank you for joining the thousands who have recognized CSI as leading industry with superior tools, training, and technology for PDM and RBM applications. We look forward to assisting you achieve success in your future endeavors.